Welcome to Module Scheduling of the Fundamentals of Operating Systems course. I'm Dr. Tim R. Norton, and I will be your instructor for this module.
The unauthorized reproduction or distribution of this copyrighted work is illegal. Criminal copyright infringement, including infringement without monetary gain, is investigated by the FBI and is punishable by up to 5 years in federal prison and a fine of $250,000.
If you have any questions, please use the question comment box you see on this page. Let's get started. What are the topics in this course, in this module of the course? Introduction to scheduling. What is scheduling all about? What types of schedulers are there? What is policy and what is the mechanisms to implement that policy? What is thread scheduling and how does that differ? So let's get started. What is scheduling? Scheduling is really selecting the thread or process to run on a processor. So the operating system manages the threads or the processes in that environment and has to select one to run on a processor. It could be a process or it could be a thread depending on the architecture of the operating system. It could be a single or a multi-processor system. So the operating system may only have one choice of processor to use, or it may have multiple. The objectives of all operating systems are to get work done for a specific reason. So throughput, response time, fairness, all of these are different philosophies that may be the underlying motivations for the design of a particular operating system. So a process is in an operating system that the operating system uses to control or manage or keep track of work. This is what is the designation in most Unix and Linux environments. A thread is in some operating systems that is inside of a process. Windows, ZOS, and some Unix implement threads at the operating system level. These are different than user threads. These are kernel threads. So we'll consider process scheduling first, and then after we've done that, we'll look at how that's different from thread scheduling and look at what thread scheduling really means. How does the OS select something to run? Here we are, we're running a computer, an operating system is running. The users have requested many applications to be active on that computer. There's only one processor. How does the operating system pick what needs to run at any particular point on that one processor, even though the user thinks there are many things running? Usually, there's some notion of priority. This isn't always the case, but most operating systems have some level of prioritization within the processes. For example, the Unix environments or Linux environments are much more focused on process priority. Windows environments are less focused on priority, but they have priority in the mechanism. So if you look at the tasks in Windows, you'll see that almost all of them are running at normal priority. But there's a way to change that to make it higher or lower, where in the Unix environment, things can be at much different levels of priority. Unix has this concept of fairness, where every process gets a chance to run, and that operating system is very much focused on making sure that all of the processes out there have some time to run. Some operating systems may allocate execution time slices so that there's this either the concept of fairness or prioritization can be implemented using the length of the time slice to control how much processor time any given process gets. So how does the operating system select a process? Well, first it has to be in memory. You can't run a program that's not available in memory so that you can fetch those instructions. It has to be in a ready state. So remember we talked about the different states of a process. If that process is waiting for an I/O to complete, there's no point in trying to dispatch it onto a processor because it's still waiting. It doesn't have anything to do. And it has to be next based on whatever policy or algorithm the operating system wants to use to select the next available process. Throughput, response time, etc. Remember, those are different philosophies that can be used in the implementation of that scheduling algorithm policy. So, when do we schedule? Well, when a process is running completes, we need to schedule something else to run after it. When a process does I.O. Now, you wouldn't think, well, why do we need to pick something else? That I.O. is really quick. But from the point of view of the processor, that I.O. takes a very long time. So the process is going to be put onto the waiting queue, waiting for that I.O. to finish, and the processor is going to sit there idle for a very long time from its perspective. So the operating system wants to dispatch or run another process while that I.O. is completing. The time slice expires. So if the operating system implements time slices, then that process's turn is up. That's what a time slice is. It says you get so many milliseconds or whatever for each turn, and then it would be somebody else's turn. Or a higher priority process. This is an interruptive technique where the process comes in and becomes ready. It may be at a higher priority, so it bumps the process that's active, forces that process back to the ready state, and then it runs for a while. Or there may be an interrupt. So when the I.O. completes, that interrupts the operating system. That's a very high priority piece of work. So the operating system is going to stop running a user process in order to run the interrupt handling software that will deal with that in communication to the hardware device. Because, again, remember, hardware devices often have very critical timing considerations, so we can't wait for the processor to not have anything to do. We have to interrupt what's going on and handle that interrupt when it comes in. Now, scheduling versus dispatching. What is the difference between scheduling a process and dispatching a process? Well, scheduling is selecting the process that's next to run. The process based on whatever the philosophy is, the priority, timeshares, fairness, whatever. Scheduling the next one is picking the next one to run. Dispatching is actually activating it on a processor. In other words, making it run on the processor. So first the operating system has to schedule a process, and then it dispatches a process. So it's very common to see that in an operating system implementation, there is one scheduler, but there is a dispatcher for each physical processor, or each logical processor in the case of something like hyperthreading. And that dispatcher controls activating a process on that particular processor. These are very separate functions in most operating systems. A single scheduler, but one dispatcher for each processor. So the dispatcher looks at the single processor, and when that processor has nothing to do, it still needs to be running some code. That's the dispatcher. So you'll see that manifest itself differently in different operating systems. For example, you may see it as an idle process or system idle. The dispatcher then calls the scheduler to get a process to run. If the scheduler says, well, there's nothing available, the dispatcher goes back to this idle process. If the scheduler says, here's the next process to run, the dispatcher can then take that process and restore its registers, all of that information that's kept within the PCB in the process control block, move it into the registers of the microprocessor, and branch to the location. First, it'll set the processor into user mode because the dispatcher is going to be running at a privilege level. It's part of the operating system. Sets the processor mode, if this hardware supports it, to user mode, and then branches to the next instruction that was saved in the PCB. So that's how the operating system dispatches or activates a program onto a specific processor. Now, when we return from the dispatcher, when the process gives up control, what happens? This can happen because of an I/O, a system call, an interrupt, the time slice is over, any number of things. But now the process is giving up the processor, and the dispatcher has to do something about it. He can either let the process finish its time slice, in other words, it becomes the next thing to run when this event is over, or, and that's based on this fairness as a major goal, or it can go back to the scheduler and say, give me the next process that meets the criteria. And that's more of a priority as a major goal. So you can see right there, that simple difference changes the way the operating system reacts to work. And that design characteristic is built in to the functionality of the operating system. Now, what are the different types of schedulers? Well, we have batch schedulers that are usually focused on throughput, turnaround time, keeping the CPU really, really busy. And this comes out of the old mainframe days, when that computer that took up the whole room or multiple rooms cost tens and tens of millions of dollars and was a very, very expensive asset. You wanted to keep it as busy as you could. You wanted to get as much through it as you could. Then we have interactive types of schedulers. And these are more interested in response time and user expectations. So here the resources aren't as expensive. It's the people, the users, that are expensive. And so now the operating system goes from maximizing the resources of the hardware to maximizing the resources of the people using the system. And then there's real-time schedulers, which are meeting specific deadlines and being very, very predictable in how the system responds to physical world events. So let's look at batch scheduling algorithms. I have a number of them. There's first come, first served, shortest job first, shortest remaining time, or a three-level scheduler. So we have separate algorithms for different parts of the system and the different ways the system works. We also have round robin. We have priority. We have shortest process first. We have guaranteed. We have lottery. We have fair share, which is based again on this notion of fairness. So you can see there are many different types of scheduling algorithms depending on what that underlying philosophy is behind the operating system. Now, in a real-time scheduler, we can have hard scheduling, which is the absolute deadlines, where it's very, very critical that we complete processing by a particular point in time. We can have soft, which means an occasional missed deadline is tolerable. So the difference here in the hard arena would be back like we were talking about numerical controlled equipment, maybe a fuel injection system in the car, airplane safety systems, where a soft scheduling algorithm might be more focused on multimedia. And if you occasionally missed a frame in the movie, well, you know, it's not great, but you may not even notice it if it's just very occasional. Then we look at rate monotonic, and that's a technique of doing real-time scheduling that allows the operating system to meet that guarantee that we've been talking about. It's not that the operating system has to react quickly. It has to react in such a way as to guarantee the completion of certain tasks by the deadlines for whatever the requirements are. And there's earliest deadline first. So these two scheduling algorithms we'll look at in a little bit to see just how they're different and how they can meet or not meet certain deadlines. So first let's look at policy versus mechanism. The policy really sets the overall objectives. It determines the philosophy behind what the operating system is trying to do. The mechanism is the implementation of that policy. It allows changes to the objectives, but within that philosophy of the objectives of the operating system. So a process can run lower a process can lower a child process priority. So that's a mechanism within that policy. The policy says that you get a certain priority, and the mechanism allows you to lower a priority of a child process you created, but not increase it above the original parent priority. A user can adjust priority from a default, or operators can change it through some global response. So this mechanism says what is allowed to change. In the case of an operator change, you may have a privileged operator that can change the priority higher, but a normal operator can only change the priority lower. That's all defined in the policy that sets those overall objectives and controls within the operating system philosophy. Now, how does thread scheduling differ from process scheduling? Well, when we look at user threads, we're talking about threads that are within a process. And they're not scheduled by the operating system. They're scheduled by that runtime environment that's within the process. We look at kernel threads, and they're process scheduling the same as they're scheduled the same as processes are from the point of view of the kernel. So, scheduling a user thread means the OS schedules the process, and then the runtime scheduler in that process gets control, and it selects the thread to run based on the policy of that runtime module. Then the runtime activates the thread. So here we see the kernel is going to schedule this process, process A. But that's all the kernel knows about. It knows about the process, doesn't know about these individual threads within the process. It's the runtime then that picks thread number 2 to run. Thread 1 and thread 3 can't run at the same time because this process has been dispatched on a processor. This thread can't be dispatched on another one because the kernel doesn't know about it. Now, when we look at kernel threads and how they're scheduled, we can see that the OS schedules the thread directly. The dispatcher activates the thread, which means that the dispatcher can activate a thread in a different process on a different processor. Now, when we look at kernel versus user thread scheduling, we see that it's simpler to design an operating system that doesn't have to worry about threads, that just allows any threads to be user-level threads, makes a simpler operating system, but there's no multitasking in the process. So that impacts the productivity of the environment and the capabilities of an individual application. And the runtime scheduler has to be designed for the application or as some generalized package that sits in that operating system environment. So kernel threads, on the other hand, are more complex to design in the operating system. The process threads can run in parallel, and the OS scheduler applies the same policy across all of the threads. So in the user thread environment, one application could use one user thread package, the other application could use another, and there would not be consistency. In a kernel threads environment, the same policy is applied across all of the threads. Here's a quiz for this module, so take a look at it, and when you're ready, resume and we'll go over the answers. Okay, let's see how we did. Each OS has scheduling objectives. Absolutely. Each operating system has a fundamental philosophy. And that's one of the major differences between the different operating systems. Is not the way they're implemented, but that underlying philosophy. And if you understand that underlying philosophy, it makes it much easier to see why an operating system behaves differently and how you can take advantage of that behavior and what might be the more appropriate operating system for your particular application or implementation. Now, OS schedules a unit of execution. That's correct. Scheduling algorithm is always based on priority. That's not correct, because there are many other techniques that can be used to decide which process or thread to schedule next. An out-ready process can be scheduled. Why not? Because it's out. Even though it's ready to run, it's out of memory. It needs to be moved from the out-ready state to the ready state, which means swapped back into memory, before it can actually be scheduled. The scheduler determines the next process to run. That's correct. The scheduler activates a process on the processor. No, the dispatcher does the activation. The scheduler just determines the next process, and it's up to the dispatcher for the individual processor to actually activate that process on that processor. User threads in the same process cannot multitask. That's generally the case. There are a very few exceptions to that, but generally the case is that user threads within the same process are being dispatched by the process being dispatched on a processor, and they can't run together. Kernel threads complicates the OS design. This is true. And lottery is a type of real-time scheduler. No, it's not. Lottery is a different approach to scheduling than real-time scheduling. So what did we talk about in this class, in this module? We looked at operating system scheduling by looking at how the operating system determines what process to run next. How does it select the work to run on a processor? We looked at an introduction to scheduling to see how it applies across all operating systems, and the different types of schedulers to see that there's more than just a few types. There are many different types with different objectives, different reasons to implement scheduling in different operating systems. We looked at policy versus mechanism to see how we set objectives through the policy we define and then implement mechanisms to enforce and manipulate that policy. And we looked at, lastly, thread scheduling to see how that's different and behaves differently, but also how it's very similar to process scheduling. Well, if you have any questions, I hope you use the question and comment box. And thanks for joining us.